right, hello software engineers. This is the last design patterns lecture on structural design patterns. Let's go ahead, jump right into it, get started, and let's see where we go. So structural design patterns are about how we combine multiple classes. And the first example we're going to look at is how we combine existing classes and make them work with potentially new or adapt an existing class to adhere to a legacy interface. So you may hear this term in programming a bit, legacy. And the idea of a legacy class or a legacy system or legacy data, it means that it's something that is already existing, may be ingrained deeply within the system. It may be hard to remove. It is something that has been in the system longer than certainly the code you're adding. And often what we may find is that we need to make changes to legacy code to implement a new feature. But there we have a problem, because we've talked about how changes can propagate. You know, going back again to the still pond. We want to drop a stone and not have it propagate. But especially if that legacy code were maybe built in a big ball of mud type way where there wasn't a planned architecture, this may be difficult to do. And short of re-implementing the entire system, you can't change that. And so the idea is you want to make some legacy class adhere to a new interface without breaking its existing dependencies or having to worry about change propagation. That is, there are still parts of the system that use the old interface. So you need to preserve both the old interface and the new interface. Can anyone think of a way to do that? Go ahead and pause this video for a second and see if you can come up with a solution. I'm assuming you've taken some time to think about it. Well, let's take a look at a physical product that is related to this problem. See, many electronic devices rely on some form of USB, say micro USB, just standard USB, USB-C. That is, my phone is USB-C, but a couple phones ago I had a micro USB phone. Well, what if you only have a USB charge cable, but it doesn't work with USB-C? Do you just have to throw the cable away and go buy a new one? No, instead you can buy one of these things, an adapter. The adapter would plug on to the USB, and then it would effectively convert the old interface, because USB is an older interface, the old interface into USB-C, the new interface. This is called an adapter. You may get an adapter, for example, if you travel overseas. That way your existing legacy charge cables, which rely on the standard US 220 watt outlet, instead can be used on, say, European outlets or Asian outlets or Australian outlets, any of those, right? That is what we mean by an adapter. And this is a design pattern where the client will use the new interface, the adapter interface, and the adapter, you could think of it like a go-between between the client and the thing that is being adapted. So the class, the legacy class, is still there. It still has the same interface. We are effectively creating a second translated interface that will instead be useful, that the client will interact with. And I do have a code example of this. Let's imagine that we have two classes that deal with drawing something. We have a class that draws a line, and we have a class that draws a rectangle. Now, the line is going to have, x1, y1, and x2, y2, and we draw a line between those points. Similarly, a rectangle is going to have 4 int arguments, but they behave differently. Rather than specifying x1, y1, x2, y2, we specify a center coordinate, x2 and y, and we specify a width and a height, and we draw that rectangle in that way. Now, these two interfaces broadly are doing something similar, right? They're drawing a shape, but they're very different. Yes, they both take in 4 integers, but they use those integers differently. But what if, for the sake of making it easier to add shapes later, we want to design a new interface? And this interface we're going to use, called shape, specifies that the draw function is simply going to take in an x1, x2, and a y1, y2, and is going, that forms a rectangle, with the bottom left corner or bottom, whichever corner being x1, y1, and the opposite corner being y1, y2. And within that shape is where we draw, or in that rectangle is where we draw whatever shape we want. So if it's a line, it simply goes from one corner to the opposite corner. If it's a triangle, we fit the triangle within that shape. If it's a circle or an oval, same thing. And if it's a rectangle, well, we just draw that rectangle. We standardize the interface. But we have this legacy rectangle, which isn't drawn that way, which isn't drawn in x1, y1. So what should we do? Should we change this function so that way instead of x, y with height, x1, y1, x2, y2? If we do that, we're changing an interface. And as we said before, when we change an interface, changes will almost necessarily propagate. So how can we make this class adhere to the new interface without breaking the old interface? By creating an adapter. Specifically, we create a class called rectangle. This class contains a legacy rectangle that is being adapted. We'll call it adaptee. And it calls the draw function, and this is where the mathematical translation occurs, where we specify the bottom left corner, and then we specify the top right corner, for example. And we draw the rectangle there. So this is still going to find, I should say it draws a rectangle from the bottom left corner. Here's how we find the bottom left corner, the min of x1, x2, the min of y1, y2. Here's how we find the width. Just subtract those. Here's how we find the height. Just like that. And now, when the client interacts with a class, the client is simply going to use the new interface, the shapes interface, which just calls draw x1, y1, x2, y2. And they don't need to worry about the fact that there's this mathematically complicated translation occurring. If instead we force the user to use the old interface and shoehorn it into the new interface, they might have to write code like this, which is pretty scary looking. So the adapter kind of just plugs in to the existing class without changing it. It contains an instance of the class being adapted, but it presents the newer interface. So now the object, we can still have the legacy code use the legacy interface, but new development can build on the new interface, and we don't have to worry about making changes that could propagate later. That is the adapter design pattern, and it turns out to be quite useful. Now let's consider another problem. Let's say that you're building a side-scrolling space shooter game, and you have a playable character, that's PC ship, not a politically correct ship or a personal computer ship, but a playable character ship. You have a set of non-playable character enemy ships. There's a set of power-ups that you pick up. These power-ups change your ship. They change the movement, the weapon type, the power. Right? Well, how would we define this in an object-oriented scenario? We could define class ship. What fields and methods would we need? Well, if you think about all the potential power-ups that we could have, or all the potential enemy ships, because remember, this class could define both the player ship and the enemy ships. There's a lot of potential modifications here. Let's consider another example. Let's say we're making a role-playing game with like Tolkien-like classes. So human, elf, dwarf. Well, we might have the starting class be human, and then they can upgrade to human warrior. And then they can upgrade to supreme human warrior. And then we could have elf and elf warrior and supreme elf warrior. And, these behaviors are similar but different. So, for example, the warrior, the human warrior, or the elf warrior, whichever one, When it wants to do damage, it rolls 2d6s. That is 2 dice with 6 sides. But the Supreme Warrior rolls 2d8s, dice with 8 sides, and adds 2 to the damage. So they do more. We could do this in an object-oriented way with inheritance, where we could say something like Human Warrior extends Human, and Supreme Human Warrior extends Human Warrior. But now we have a lot of methods overriding, and the other problem we have is, there's not just warrior classes, there's ranger classes and wizard classes, although, granted, wizards are not humans in the Tolkien universe. They are Maya, and that's a separate thing. And I'm just going to shut up now about the Tolkien universe. The point is, if we do this in this object-oriented way, every class is going to have to be, or every change that we make, every upgrade is going to have to be its own class. The same way that maybe with the ship, every weapon upgrade is going to have to potentially be its own class. So ship with turbo laser, ship with minigun, ship with spread gun. Like, we're proliferating classes here. We're making a lot of classes. And while that's not inherently bad, a lot of this code might be redundant, which we can limit a bit with abstraction, but that means we have a lot more classes to keep track of. Would MVC work to solve this problem? Can anyone think of a way that maybe we could use MVC to solve this problem? Well, we could have a very heavyweight controller that manages all the actions and interactions between each of these entities. It handles the input, it handles the calculations. We then have a lightweight model that's just basic information about a given game object, and a very, very lightweight view, if we even have it, if it's not just command line, which is the draw part of the game loop. We could do it that way. But let's, for a moment, think about another strategy. And here, let's say that you're doing beverages for a coffee shop, and you have, several different types of drinks. For now, let's just actually simplify it and just say coffee and tea. But we have a number of ingredients that we can add. And each of these ingredients costs a little bit of extra money. You don't get whipped milk for free. You gotta pay a little extra for the whipped milk. And you want some cost function to calculate the price of the base coffee plus whatever ingredients you add. This is a fairly simple example. And we want to avoid class explosions. So we don't want something like house blend. We don't want something like house blend. And then house blend with whipped milk extends house blend. And house blend with steamed milk. Especially if we could maybe mix, say, soy and whipped milk. Or mocha and whipped milk. Or maybe add a shot of espresso and whipped milk to a house blend. Any number of combinations. We want to be able to dynamically combine a bunch of different things. So to this end, we're going to define, and again, we could define this as each different drink starts as a subclass. They each have Boolean fields. They're Boolean if they're turned on. We have these methods. We have cost. What's the issue with this? Well, if we add ingredients, we have to add an ingredient to every single class. We have to add this method to every single class. So, we want to avoid a class explosion. So how can we do this? It's with a decorator design pattern, and it takes a single core object, and it decorates it to add features, attributes, and functionality. So, how does this work? Well, first, let's look at the class diagram that we have here. And this is for how you do Java input streams, like Java file I.O. So you might do something like a file input stream, and then you might do a buffered input stream on top of, notice iStream is a file input stream, on top of iStream. So you start with, okay, here's your file input stream. And then you wrap that, you put that inside of another object called a buffered input stream. And you've probably seen something like this before. Let's look at another example. And this one is a bit sillier. This goes to the drink. I have a class called drink. And this class has two abstract methods. It's an abstract class. Two abstract methods, get price and toString. And I have coffee. For now, just generic coffee. Costs $2, and if I return it as a string, it returns coffee. Not a particularly complicated class. And I also have tea, Get price, $1.50. It's a little cheaper. And if you return a string, it returns T. And both of these are extending this abstract class drink. But now I get into the decoration. I want to be able to add ingredients like milk, espresso shots, honey, whatever. How can I do that? Well, I define an abstract class called ingredient, which extends drink and contains a base drink. So that means that this class is going to have get price, and it's going to have toString, but it also has a base drink. And from there, I can add ingredients like milk, which costs 25 cents, and adds to whatever the string is with milk. So it might be coffee with milk, tea with milk. I can also add cream, which extends milk. So it adds cream is 25 cents on top of milk's price. And I can add to the base drink with cream instead of with milk. And I also have espresso, so add an espresso shot. So how can I actually use this? What do I actually do with this? Well, I can do something like drink tea equals new tea. Pretty straightforward. But then I can do drink coffee with milk. And look at this line of code, how I generate that coffee with milk. I start by making a coffee, just a plain old boring coffee. I then put that coffee into this milk object. So now this is a milk object, but the base drink is coffee. And if I print this out, so print coffee with milk toString costs and get the price, well, the milk costs 25 cents, the coffee costs $2, so this should print milk with coffee costs $2.25. And that is indeed what it prints. I could also, you want a double shot, a coffee with a double shot of espresso, new espresso, new espresso, new espresso, new coffee. Right? And so, this is the decorator pattern. We decorate an object not by adding fields to the object or adding methods, but by wrapping that object inside of a decorator class. And the decorator class and the base component, whatever it is, both ultimately extend, albeit to different levels of inheritance, ultimately extend some abstract base component. So in the case of here, we have filter input stream, and then we have buffered input stream and data input stream as different things that are decorations. So our base might be something like a file input stream. We decorate that base with a buffered input stream, like we do here. This is why if you're doing file I/O in Java, it can sometimes look a little bit crazy, a little bit over the top, because you might do something like file f equals new file something dot text. But then to actually read the file, you would create a buffered file reader, BFR, which is equal to new buffered file reader, new new buffered reader, not buffered file reader. Sorry. Buffered reader, new file reader F. And you'll notice that this, remember F is a file. This could all be written on one line of code, and it looks a bit wonky. This is like a very Java thing to write. By the way, the red underline here is just because I'm not throwing exceptions, so just to make it go away, I can just do that for now. This is a decorator pattern, and it's decorated because you can choose to read the file in different ways. You can also Rather than a buffered reader up here, you could do something like a data input reader, a data reader. You can also read, rather than a buffered way, just read 1 byte at a time, however you want to do that. But this is the Java way typically of doing file I/O, and it uses a decorator pattern. So why do we do this? This looks, well, one, it kind of looks cool, right? Like, this looks pretty cool, and it seems like a pretty simple way to describe a double shot of espresso. This lets us create fewer classes, because rather than having to create a class, a coffee with espresso, coffee with double shot espresso, we just create a bunch of kind of pieces of classes and just dynamically put them together at runtime. So we're kind of manufacturing classes as we go. And so this is the decorator pattern is often used in Java I/O for input outputs. There's many stream types that are wrappers. You can do things like pushback, line numbering, buffering. All of these are different types of file readers, but they're decorators on the existing file reader. And this also, by the way, this decorator is used in Java Swing. And the basis of this, often, one architecture that takes decorator extreme, is entity component systems. And this is often used in gaming. The idea is that it's a pattern in which each object in the world is completely unique, as in represented by a single primary key element. So it works kind of like a database, where every entity is like a record in a database. Now, this might be a bit hard to swallow, because we were talking about objects a second ago, and how objects interacting. Well, what is an entity? An entity is a globally unique number. For every discernible thing in the game world, there is exactly one entity. Not a class, but a single entity. And the entity doesn't actually have any data and no methods. And you may be thinking, well, wait, how are we representing that then? The component provides any aspect to the state of an entity. So, want the entity to have a position in the world? You give it a spatial component. If you don't need the entity to be in the game world, you just need to do something else without a particular position, you don't give it this component. You want entity to have health? Give it a health component. Does it have a velocity? Give it a velocity component. Right? If something doesn't move, you don't need to give it a velocity component at all. And so all the data goes into the components. All of it is, and I like the way he says that. So you might think like, okay, but really common things like XYZ, why don't we just put that in the entity? No, because as soon as you start migrating data into the entity, you've lost. It should be in the component. Why is this? Because it abstracts everything away. The entity is just a place to hang stuff, and that stuff can be whatever you need it to be based on the components. Each entity combines the components it needs, and so rather than having to define, for every enemy, a class that handles it, and if there's variations on that enemy, a separate class, maybe an inheritance class, and create that structure, instead you just create components, and you add those to the entity. So the entity is just a primary key. So then how do things get updated? Well, you update them by using a system. So a system is a cohesive set of functionality that does all of one thing in the game. That's collision detection, player input, enemy AI, rendering, enemy spawn, physics. And the idea is the render system relates to the position, sprite, and camera components. The render system doesn't relate to the animation. That's in the animation system, which also handles sprites. The physics system, shape, rigid body. Control system, position and controls. AI system, position and enemy. You get the idea. This would be the way that we would design, or this is, I should say, the systems that interact with these components. So you look at the entities, you look at if the entity has an animation component, then the animation system needs to work with that entity. That system would also need a sprite component. So that is an extreme version of decorators, where the base class is literally just a foundation to build on. There's no starting data, and all the data is added as components. And that's a pretty extreme version, but it makes your program much, much, much more modular because you can just plug and play things. So that's the idea. So that is our last video on design patterns. That is by no means all the design patterns. There are so many more. We're going to talk about another one on Tuesday that's structural called a bridge. We're not asking you to memorize these. But what we're trying to show you is that there are practical reasons to have these design patterns. They solve specific problems. The decorator design pattern can solve the problem of having a class explosion by thinking of classes as components that all kind of latch onto each other, onto a single base entity. With that, thank you all for watching, and I will see you next time. Take care.